In this unit, we will discuss magnetism and learn about magnetic fields and different magnetic objects. All magnets have a north pole and a south pole as well as a magnetic field. The magnetic field is the space near a magnet, and it consists of invisible field lines that always travel from north to south. The Earth is a large natural magnet. It has a magnetic field running from the geographic North Pole to the geographic South Pole. Geographic means as indicated on a map. As opposite poles attract each other, the Earth's magnetic South Pole is underneath the North Pole at the top, and the magnetic North Pole is underneath the South Pole at the bottom. Look at the images of the geographic North and the magnetic South Pole. Paste your pages and write the new words in your worksheet. Alloy. The quality derived from the combination of two or more metals melted together. Corrode. To destroy metal with exposure to air and water. Rust. Ferrous metal. A metal that contains iron. Magnetic lines. Invisible lines used to visualize magnetic fields. Magnetism. The ability of an object to exert a pulling, attracting, or pushing, repelling force caused by a magnetic field, magnetic lines. Malleable. A metal that can be hammered or pressed into shapes. Non-ferrous metal. A metal that does not contain any iron. Poles. The ends of a magnet at which the magnetic field is the strongest. Recycle. To remove waste materials and convert them into new products. Reduce. To lessen the amount of waste people create by buying and using fewer disposable goods. Reuse. To use a product, for example, glass, again for the same or another purpose in order to reduce the amount of waste created by only using it once before disposing of it. Substance. The matter that something consists of.
What is a magnet? For kids. Do you know what these are? If you said magnets, you are right. Magnets are used in many places for many things. And today, we are going to learn more about them. So what exactly is a magnet? Magnets are pieces of metal, usually iron or steel, that are able to attract certain kinds of other metals. The force drawing objects to a magnet is called magnetism. And the area surrounding a magnet is called a magnetic field. Pieces of metal like iron or steel can be pulled to a magnet. This is called attraction. When this happens, the metal will stick to the magnet like glue. There are two ends on each magnet. One is called the North Pole, and the other is called the South Pole. Want to know an interesting fact? The North and South poles of a magnet are attracted to each other and will always be pulled towards each other when they are near the other. But the same poles of two different magnets will push apart or repel the other. Let's test this out. First, let's try putting two North Poles together. Look at that. They are repelling each other. How about two South Poles? They also repel each other. Now, let's try putting a North Pole and a South Pole together. Can you guess what is about to happen? You are right. They are sticking together because they are attracted to each other. Cool, right? There are three different types of magnets: temporary magnets, permanent magnets, and electromagnets. Temporary magnets become magnetized when a magnetic field is present and lose their magnetism when the field is taken away. Like when you rub a magnet against another piece of metal, like a paperclip or a nail. Permanent magnets are made from materials like iron or nickel that are naturally or chemically magnetized and already have their own magnetic fields, like the magnets you use on your refrigerator. Electromagnets are created by running an electrical current through a coil with a metal core. The energized core creates a magnetic field, and when the current is shut off, the magnetic field disappears. An MRI machine is an example of an electromagnet. Electronics like TVs and computers also use this kind of technology. Magnets are used in many places for many things, not just to hang up your schoolwork on the refrigerator. They are used in speakers, computers, motors, doorbells, telephones, compasses, and tools. They are also used in doors, by recycling centers, hospitals, and lots of other places. And here is one final interesting fact. The Earth's core is made of iron and nickel, so it creates its own magnetic field. Wow, magnets are pretty awesome, right? Now that you know more about magnets, let's test your new knowledge. How many types of magnets are there? 3. Temporary, permanent, and electromagnetic. Fill in the blank. The area surrounding a magnet is called a magnetic blank. Magnetic field. True or false? The Earth's core has its own magnetic field. True. What happens when two south poles of a magnet are near each other? They repel or push apart each other. An MRI is an example of which type of magnet? Electromagnet. Magnificent job, magnet mavens! Whether you are doing a science experiment or sticking your latest piece of artwork on the fridge, magnets are all around. At some point, you have probably used a magnet and not even known it. But now that you know more about them, you will be able to spot magnets in even the most random of places.
Properties of magnets. How can we observe the invisible magnetic fields of a magnet? A magnetic field is the area around a magnet that has a magnetic force. We can observe the magnetic field of a magnet using iron filings. Place a bar magnet on the top and cover it with a sheet of paper. Gently sprinkle iron filings over the paper. Tap the paper to spread the filings out. Wow! There it is! Notice that the magnetic field is strongest at each of the poles. Let's see what happens when we add a second bar magnet and bring two like poles close together. Look! The space between the poles doesn't have many iron filings. This is because the poles are repelling each other. What do you think we'll observe when unlike poles are brought close together? Cool! The iron filings are concentrated between the unlike poles because they attract each other. Experiment by adding more magnets. Arrange them in different ways and observe the different patterns their field lines produce. Check out our related videos to observe other ways magnets interact with other objects. That was fun! See you next time!
Lesson 14. Magnetism. Magnetism is a physical phenomenon exhibited by a magnetic field. A magnet has two poles, namely a north pole, plus, and a south pole, minus. A magnetic field forms around a magnet and moves in a determined direction from the north pole, plus, to the south pole, minus, of the magnet. Magnets either attract or repel other objects with magnetic properties. If we place the two, like plus and plus or minus and minus, poles of two magnets together, they will push, repel, each other away because both have the same polarity. If we place the two unlike, plus and minus, poles of two magnets together, they will pull, attract, each other together. Types of magnets. Magnets can either be permanent or temporary magnets. Permanent magnets, as indicated by the name, have a permanent magnetic field and keep their magnetism for a long time, for example, a bar magnet. Temporary magnets don't have a permanent magnetic field and only become magnetic in the presence of a permanent magnet. An electromagnet is an example of a temporary magnet. As long as there is an electric current flowing through the magnet, it has a magnetic field. As soon as the current is turned off, the magnetic field disappears. Lesson 15. Investigate magnetism. All materials are either magnetic or non-magnetic, and only certain types of materials attract to magnets. Magnets attract the iron components in certain materials. Ferrous metals, also known as ferrite, are magnetic and contain iron, while non-ferrous, also known as non-ferrite, metals do not contain iron. Magnets only work with ferrous metals. Pace the activity and listen to the information. Plastic is not magnetic because it does not contain iron, nickel, or another magnetic metal. A magnet will not attract a plastic ruler. Wood is not magnetic because it is a natural material that does not contain magnetic metal. A magnet will not attract a wooden pencil. Glass is not magnetic because it does not contain iron or another magnetic metal. A magnet will not attract a glass object. Aluminium foil is not magnetic because aluminium is a non-ferrous metal and does not contain iron. It will not be attracted to an ordinary magnet. Iron is magnetic because it is a ferrous metal. A magnet will strongly attract an iron object such as a paper clip. Steel is magnetic because most steel contains iron. A magnet will attract an ordinary steel object such as a spanner. Nickel is magnetic because it is one of the metals that can be attracted to a magnet. Silver is not magnetic because it does not contain iron and is a non-ferrous metal. A magnet will not attract a silver object. Copper is not magnetic because it is a non-ferrous metal and does not contain iron. A magnet will not attract copper wire. Lead is not magnetic because it is a non-ferrous metal and does not contain iron. A magnet will not attract a lead object. Yellow copper is not magnetic because it is usually brass, which is made from copper and zinc. It does not contain iron, so an ordinary magnet will not attract it. Aluminium is not magnetic because it is a non-ferrous metal and does not contain iron. An aluminium will not be attracted to an ordinary magnet. Lesson 16. Recycling. Recycling is the process of breaking down waste material to its smallest parts and converting it into new materials or objects that may be used again. South Africa's approach to recycling has not yet accelerated to the rate of that in more developed countries, as we do not yet have the same formal recycling infrastructures in place. The collecting and selling of waste materials, for example, glass, paper, Plastic or metal/aluminum for recycling is becoming a thriving informal industry that provides jobs for more than 100,000 people as more and more people are showing an active concern for the environment and the impact that our overfull landfills has on it. Plastic is still a growing concern with regard to recycling and waste management. It is difficult to identify and sort the different types of plastic, and the demand for recycled plastic is very low relative to other recycled materials. After you have completed this unit, you must be able to demonstrate your knowledge and understanding of simple electrical circuits, electrical components and their symbols, electrical circuits and circuit diagrams, series circuits, parallel circuits, combined circuits, electromagnets. Paste the worksheet and write down your important terminology. AC, alternating current, an electric current that constantly reverses direction in a circuit, commonly 220 V used to power household appliances. Circuit diagram, a graphical representation of an electrical circuit using symbols to indicate components. Component, any electrical device such as a resistor that has electrical characteristics and that may be connected to a circuit. Conductor, a material that allows the free flow of electric current to conduct heat, light, or sound. Current, the flow of electricity, measured in ampere. DC, direct current, an electric current that flows in one direction only, commonly 12 V used in batteries, etc. Insulator, a material that doesn't conduct electric current and is used for protection against electricity. LED, light-emitting diode. Solenoid, a coil of wire that acts like a magnet when an electric current passes through it. Voltage, the difference in electric potential between 2 points in an electrical circuit, measured in volts. Paste the image in your book. Fill in the missing information. Color in the wires the correct call.
Or.
The earth leakage. Each house and business in South Africa has an earth leakage in the electrical distribution board. It is a safety device that detects a short circuit. If there is a short circuit, the current supply, 220 volt, immediately cuts off the electricity supply to the house or business. Ensure that you know where the earth leakage is located in the electrical distribution board. Do a test at least twice annually by pressing the test switch. The earth leakage switch must switch off, fall to the bottom when you do this test. To reconnect, push the switch down completely and then return it to its normal position. Paste the worksheet and fill in the missing information. Draw the symbols. Remember to draw them in pencil and also use a ruler. Series circuits. When the positive plus symbol terminal of a component is connected to the negative minus terminal of the next component in an electrical circuit, it is called a series circuit. The current in a series circuit, measured in ampere, A, is the same through each of the components, and the voltage, measured in volts, V, is divided between the components. Adding more lamps, light bulbs, to the circuit will increase the resistance, and the lamps will not shine as brightly. If one lamp fails, the current will not be able to flow, and the remaining lamps will not shine. Adding more lamps, light bulbs, to the circuit will increase the resistance, and the lamps will not shine as brightly. If one lamp fails, the current will not be able to flow, and the remaining lamps will not shine. Lamps connected in parallel shine equally brightly. If one lamp fails, the remaining lamps will continue to shine because the current is able to flow along another path. The same principles still apply to components connected in series and parallel in a combined circuit. Electromagnets. Electromagnets consist of insulated wire wound into a coil around a metal core. The more coils wound around the core, the stronger the magnet. An electromagnet has a magnetic field as long as there is an electric current flowing through it. If the current is interrupted or switched off, the magnetic field disappears. In this unit, we will discuss mechanical systems and control. Machines provide a mechanical advantage, also known as MA, to make work easier. A mechanism or machine makes it easier to perform a task. Cranks. A crank consists of an arm or handle attached at a right angle, normally 90 degrees, to a rotating shaft or crankshaft, which is connected to and rotates around an axle or a crank. The crank makes it possible to exert a large force on the shaft and gain mechanical advantage. A crank converts rotary motion into linear motion. For example, the crank in between bicycle pedals and the chainring mechanism that pulls the chain to drive the bicycle motion forward. Pulleys. A pulley is a wheel with a groove that allows a rope, cable, belt, or chain to run over the pulley inside the groove. The wheel turns on an axle or shaft. A flexible rope, cable, or strap transfers movement or force from one end to another. Pulleys are used to move objects horizontally or vertically. Because pulley wheels turn on an axle, there is a minimum friction. Using one pulley doesn't provide any mechanical advantage. However, using a pulley system of 2 or more pulleys does provide mechanical advantage. Single-wheel pulley. Pulley system consists of 2 or more pulleys. It is used to obtain mechanical advantage as it reduces the force needed to lift heavy objects. The more pulleys in a system, the easier it is to lift heavy loads. But the further the rope has to be pulled. An example below has one pulley attached to a fixed point and one pulley attached to a moving point. One loose end of the rope is attached to the fixed pulley when the other loose end is pulled. The moving pulley moves up.
For thousands of years, mankind has been perfecting the art of lifting heavy things, manipulating the laws of physics using nothing more than a few simple tools and a bit of ingenuity to allow huge loads to be moved very easily. This is only possible because cleverly designed machines like this pulley system are able to amplify forces in some way. The amplification of a force is called mechanical advantage, and we can quantify the amount of mechanical advantage a specific system can generate as the force that is output by the system divided by the input force. To illustrate this, consider a mass of 100 kilograms. To lift it off the ground, you need to apply a force of around 1 kilonewton. But if you use a device with a mechanical advantage of 2, you only need to input a 0.5 kilonewton force. To explain how this is even possible, this video will take a look at 3 devices: levers, pulleys, and gears that are able to do just that. I've also covered a 4th way of generating mechanical advantage using hydraulic systems in a companion video that you can watch right now over on Nebula. The best way to get access to Nebula is by signing up to our bundle deal with this video's sponsor, CuriosityStream, but more about that later. Let's start with the lever. Consisting of just a beam pivoting about a fixed hinge, called the fulcrum, it's one of the simplest ways of generating mechanical advantage. Consider the amount of force we need to balance a mass located at one end of the beam. When discussing levers, it's common to talk about a load, which in this case is the mass, and an effort, which is the force that needs to be applied to lift the load. It's quite obvious that this system with the fulcrum in the middle of the beam can only be balanced if the effort is equal to the load. But what if we move the fulcrum away from the center of the beam, towards the mass? We now only need a much smaller effort to balance the lever. But why? We can explain this by considering the rotational stability of the lever. Both the load and the effort have the effect of rotating the lever, which means that they are generating moments about the fulcrum. A moment is a quantity that determines how much a force causes something to rotate about a specific point. It is calculated as the magnitude of the force multiplied by the perpendicular distance from the line of action of the force to the point of interest. For the lever to be in rotational equilibrium, the moments acting about the fulcrum must balance each other. We can then easily calculate how large the effort needs to be to balance the load, based on the distances A and B. Earlier, we defined mechanical advantage as the ratio of the output to the input force, so we can see that for a lever, it is calculated as the ratio of the 2 distances. By moving the fulcrum, we can change the mechanical advantage. Putting it very close to the load means we will be able to lift the mass with a much smaller force, which is incredibly useful. It might seem like the lever is somehow breaking the laws of physics by turning a small force into a much larger one, but it's important to remember that levers don't actually create energy. The amount of energy used to lift a mass is equal to the magnitude of the applied force, multiplied by the distance over which the force acts. So although the force applied to lift the mass when using mechanical advantage is smaller, it needs to be applied over a longer distance. The amount of energy used is always the same, with or without mechanical advantage. All devices that generate mechanical advantage work on this same principle. They convert a small force applied over a long distance into a large force applied over a short distance. The pulley, which is essentially just a wheel containing a groove through which a rope or cable can run, is a bit more difficult to understand than the lever, but opens up even more possibilities for generating mechanical advantage. Let's look at a simple configuration where a rope is passed through a single pulley and is attached to a mass. If a large enough force is applied to the end of the rope, the mass can be lifted. This system allows us to redirect the force needed to lift the mass, so that we can pull on the rope at an angle instead of having to lift the mass vertically off the ground, but it doesn't actually provide any mechanical advantage. If the mass has a weight of 1 kilonewton, a 1 kilonewton force has to be applied to the end of the rope to lift it. Because the rope is being pulled on by the applied force at one end and by the weight of the mass at the other, it's subjected to a tensile load of 1 kilonewton along its entire length. In reality, a slightly larger force will need to be applied to compensate for friction at the pulley. But to keep things simple, we'll assume that the pulley is both frictionless and massless. Let's look at a different setup now, where the pulley is flipped upside down and is attached to the mass instead of the ceiling. This small modification completely changes how the system works. It might seem impossible, but we now only need to apply half the force we previously did to lift the mass. This system has a mechanical advantage of 2. The reason is that the mass is now supported by 2 segments of rope, instead of just 1. To better understand what's happening, let's take a look at the forces acting on the pulley. There is one downwards force, the weight of 1 kilonewton, and 2 upwards forces, caused by the 2 parts of the same rope that are supporting the pulley. The tension in the rope is constant along its length, so the 2 upwards forces must be equal to each other. And for the system to be in equilibrium, they must balance the 1 kilonewton load. We can conclude that both upwards forces are equal to 0.5 kilonewtons. Since half of the load is taken by the ceiling, the load can be lifted by applying a force of only 0.5 kilonewtons to the end of the rope. To make this system slightly easier to use, we can add a second pulley, so that instead of pulling up on the free end of the rope, we can pull on it at an angle. Like with the lever, the cost of dividing the force needed to lift the mass by 2 is that we have to apply that force over double the distance. The additional distance comes from the fact that 2 segments of the rope need to be shortened to raise the mass, instead of just 1. Adding even more pulleys allows us to achieve greater mechanical advantage. This system has a mechanical advantage of 4, for example. The mass is supported by 4 rope segments, so producing an output force of 1 kilonewton only requires an input force of 0.25 kilonewtons. Because using this many pulleys takes up a lot of space, the individual pulleys are usually combined into 2 blocks. One movable block that moves with the mass, and one standing block that is fixed to the ceiling. Gears are another type of simple machine that generates mechanical advantage. The teeth of one gear interlock with identical teeth on another to form gear trains that can be used to transmit and multiply forces. In each set of gears, we can identify a driver gear that's connected to a motor or a rotating shaft and transmits force to a follower gear, causing it to rotate in the opposite direction. In this case, the follower gear, which has 20 teeth, is smaller than the driver gear, which has 40 teeth. Since the circumference of the larger gear is twice that of the smaller gear must rotate twice for every 1 rotation of the large gear. This configuration is called a speed multiplier. The follower gear is rotating twice as fast as the driver gear. To understand how gears can generate mechanical advantage, Let's look at how force is transmitted through the system. This motor provides a torque of 100 Newton meters to the driver gear. Torque is a moment that acts about a longitudinal axis and is calculated as the magnitude of the force multiplied by the distance to the axis of rotation. The torque of 100 Newton meters is equivalent to someone turning the shaft with a force of 100 newtons at a distance of 1 meter, or a force of 200 newtons at a distance of half a meter, for example. The input torque causes the driver gear to rotate, generating a tangential contact force between the two gears. We can calculate the magnitude of the contact force as the input torque divided by the distance between the force and the axis of rotation, which is just the radius of the driver gear. The contact force causes the follower gear to rotate, generating an output torque that can be calculated as the product of the contact force and the radius of the follower gear. This tells us that the mechanical advantage of the system is given by the ratio of the radii of the two gears. This is the same as the number of teeth on the follower gear divided by the number of teeth on the driver gear. With 40 teeth on the driver gear and 20 on the follower gear, this particular system has a mechanical advantage of 0.5. Doubling the speed of the follower gear comes at the cost of having the output torque. But if the smaller gear is the driver gear, the system will have a mechanical advantage of 2. The output speed is halved, but the output torque is double the input torque. Even when a system has more than 2 gears, the mechanical advantage only depends on the number of teeth on the first and last gears. This means a third gear, called an idler gear, can be added to make the driver and follower gears turn in the same direction, without affecting the mechanical advantage of the system. Using a small driver gear to turn a large follower gear and generate large torques is how a hand winch works. A drum around which a cable is wound is attached to the large follower gear, and the small gear is driven by turning a handle. The larger number of teeth on the follower gear means that the input torque from the handle is amplified, allowing heavy objects to be moved by the winch. Levers, pulleys, and gears aren't the only devices that can amplify forces. Hydraulic systems, like you would find in a hydraulic press for example, use the incompressibility of liquids to generate mechanical advantage, which makes them useful for applications like the deployment of landing gear in aircraft flight control systems.